Good afternoon and welcome to Safety System Control Architectures presented by New Equipment Digest, Machine Design, and EHS Today. Today's webinar is sponsored by Schmerzel, USA. My name is Steve Bush and I'm the Managing Editor of New Equipment Digest magazine. Before we begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's presentation, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the Help button below the slides. We welcome your questions today. Just type your question into the question window on the side of your screen and hit the Submit button. We will answer as many questions as possible during the Q&A session, which will follow the main presentation. But please feel free to send in your questions at any time. Also be aware that today's sessions are being recorded and will be available on the New Equipment Digest, Machine Design, and EHS Today websites within the next week. You will be notified by email when the archive is available. Now let me introduce today's speaker. Mike DeRosier is a TUV certified functional safety engineer for machinery. His 20 years of experience include controls engineering to design, build, and integrate full machine control systems. His safety experience led him to help corporations to develop corporate safety standards, perform machine safeguarding risk assessments, machine safety training and design, as well as implementation of safety systems for all aspects of machinery: electrical, electronic, pneumatic, hydraulic, and mechanical. Welcome, Mike. The floor is yours.
Thank you very much. Good day, everybody. Appreciate your time today, and I think we'll cover a lot of information in a short amount of time. And as mentioned, type in your questions. We'll get to the questions as best we can and talk specifically about safety system architectures. And in doing that, we're going to talk about how the safety systems really work and interact at different levels and break it down a couple of different ways. When we look at a machine, we can't just go by the safety components. I think we all know that selecting proper safety rated components to put on the machine is definitely going to improve your safety reliability on the machine, but you can't just stop at the component selection. There's more to it behind the scenes and the wiring and how it's connected. When you think about an operator's perspective, they see a door, they see the switch, they see the machine shutting down. But how that actually happens is really invisible to them. The wiring, the relays, the interconnection between them. And how that's supposed to be done is all a matter of your risk analysis and determine what the proper level or control architecture should be in the safety system itself. In deciding those factors, what you see is the selection charts, such as those listed in ISO 13849, that selects the performance level. When you look at severity of harm, frequency of exposure, and possibility of avoiding it for a particular safety function, whether it's a emergency stop function, a guard door interlock function, various safety functions in the machine, it's going to drive you to a specific performance level. And there's more to performance levels than just the components and the wiring. There are calculations and statistics and validation principles that you apply. But the core above any performance level is still designing in the proper control architecture. Those control architectures are broken down into categories. There's control category B, 1, 2, 3, and 4. When you go through that decision tree process, it's easy to make that determination based off of severity, frequency, and avoidance, but it becomes a mystery on how to actually make it work. You can select the proper safety components, the door switches, the light curtains, your emergency stops, bumpers, edges, and on the simplest form, you need to shut a motor down on the machine. And again, these are going to be more examples. There's going to be more details to it, but it could be pneumatics or hydraulic valves that you have to properly and sufficiently effectively shut down. The interconnection, a lot of people don't know what to look for and what to ask for. So in the next set of slides, we're going to break down the concepts of those different control categories of category B, 1, 2, 3, and 4. In doing that, we got three different representations. We have the symbolic representation that will show you, a pictorial, and then a schematic representation. The one thing I just want to make sure that we're clear with everybody, these aren't complete schematics that we're showing you. There's more to it. There's more technology out there. But we want to show the overall concepts to get more of a clearer or better understanding of how the flow and what you're looking for in the different control categories. So you need to look at your machines and look how they're interfaced and make a judgment call and evaluate your schematics based off of that particular machine, not just a generalization. So the first system we're going to look at on the symbolic representation is a control category B. That's your starting point. It's a very simple system. It's just a single channel, unmonitored type of system. When you look at the flow right there, you have your E-stop button. When your E-stop is pulled out, you have the ability of hitting a reset button to re-enable your circuit through a relay or contactor. And then you can perform your normal start-stop on a motor starter, a drive, an enable, whatever is needed inside that particular machine. So it's just a single path, a single channel of wiring when doing that. If we take this a little bit further, a little bit more depth in it, if I give you a little bit of a schematic diagram, but instead of electrical symbols, I throw the pictures in on there for the pictorial, you'll see how that works a little bit more, where you have the reset button latching with the E-stop to enable your contactor, that enable relay that's pictured. When that enable relay closes, you can now do your start-stop function on your normal motor starter, your motor relay, to turn that motor on and off. It's nothing but a single channel type of system. Any single fault may lead to the loss of the safety function. When we go into more of a full schematic view and representation, you see there's a little bit more behind the scenes when you create a latching circuit. For example, under the reset button, you'll see an additional contact there from the enable relay. The concept behind the circuit is you hit your reset button to close the circuit, and the enable relay will keep itself on until you hit the E-stop button. When you hit the E-stop button, you would then shut the motor down. Whether it's in a start or stop condition, you can make sure you shut that power down by breaking the enable relay contacts. This is your core. This is your basic system with a single channel, unmonitored system. You don't have any diagnostics capability with it. But when you go through your decision tree of determining what control category or what performance level is required for your particular safety function, a single channel system may be sufficient or it may not be sufficient for what you need to do. Based off of those levels, it'll take you into these different control categories. So now we're going to take our baseline, our core of control category B, we're going to step it up into control category 1. If you remember from just a couple slides ago, this doesn't look any different than control category B. And one of the first questions that comes up, well, why do we have two different categories? What's the difference between control category B and control category 1 if they're basically the same thing? They're a single channel, unmonitored system. The main difference does come into selection of components and how things are wired up. You see at the top there, we state well-tried components and well-tried safety principles. The concept of a category 1 over a category B is you're trying to reduce or eliminate some of what's referred to as the common cause failures of a machine. Failures that occur in the safety circuit could be welded contacts, a switch failing, a shorted wire. So what are some of the principles that you can do? One of those is separation of wiring. You have a switch out on your door or your e-stop out on a remote station or a rope pull, as you see pictured there, out on the machine. That device has to come back and be wired into a control cabinet, into your master control relay, your enable relay, whatever your circuit is designed to do. In doing that, typical installation, you route two wires, your feed and your return, whether it's in the same cable or conduit or trough, going back to the control cabinet. Well, you haven't eliminated the possibility of short circuits from occurring or significantly reduced them. So one of the methodologies is you run the cables in separate paths. So you have your feed wire running to one side of the switch and a return wire routing down another side of the machine into another spot in the control cabinet. Is it possible that a wire can short circuit? It's possible, but more unlikely that that could occur, so you eliminate or potentially significantly reduce a fault of a short circuit occurring inside wiring or installation of wiring to improve the reliability of your circuit. Another one is oversizing your relays or contactors. If you have a 5 horsepower motor and you put a 5 or 6 horsepower rated contactor in there, you're close to the maximum load requirements or capabilities of that relay or contactor. So your chances of arcing are much higher being close to that maximum load. Doing things such as doubling the size, put a contactor that's rated for 10 horsepower, it has a much higher current carrying capability. It doesn't mean that the contactor cannot weld or mechanically fail, but your chances or your likelihood of that occurring has been drastically reduced because you're not pitting the contacts nearly as hard or as often, so the contactor in a hardware reliability can tend to last a lot longer than one that's rated close to maximum load. So even though the circuit and design principles are the same as far as the single channel unmonitored concept, and you see the same thing in the schematic representation here, the difference does come into the selection of the hardware, oversizing, adding the separate wiring paths to reduce some of the failures that could possibly occur in your safety system. Might be a beefier type of switch or contactor that can take a little bit more of a beating on it. You see the schematic is exactly the same. So well-tried components, well-tried principles are really the key, and that's the main difference between control category B and control category 1. What has been seen in the past is a lot of people think they may be at control category 1, but without having the design principles, reality is they may only be control category B. So adding some of those design principles can really improve your overall safety system, even in a single channel scenario. The next one we get into is a control category 2. See a few more components in here. This is what's commonly referred to as a single channel monitored system, where you get some monitoring capabilities, you get some diagnostic capabilities. You have typically a single channel, whether it's a safety monitoring relay or a couple of single relays or contactors that you're working with on a control circuit, but it's a single channel system that you can monitor to determine certain failures. You can still lead to the loss of your safety function, but you're having some monitoring and indication of where that failure has occurred. Category 2 may require more mechanical checks, checks on the machine to know that the systems are functioning properly before they're required, such as opening and closing a door on the start of a shift or every hour to make sure the safety system is functioning properly. But here's where another additional requirement comes into. When you look at the contactors or relays to drive your loads, the contactors become part of the safety system. They're an extension of your safety monitoring relay. And as a result, the motor relay or those contactors are required to be mechanically linked. Now, typically you hear a couple different terms: mechanically linked, positively guided relays, force-guided relays, mirrored contacts. They're all terminology that is resulting in meeting the same thing as far as a relay or contactor being allowed to use as a safety circuit or safety function. By standard, when you have a normally open contact that welds, the normally closed has to maintain a 0.5 millimeter gap tolerance from closing again. Why that's important to us when we talk safety circuits is the monitoring capabilities. When a contactor fails and welds and stays shut, how do we know that that contactor has really failed? The normally closed, if it's allowed to close again, you can never detect it. But in a mechanically linked relay or contactor, because you have to maintain that gap, now you can feed that loop back into your safety monitoring relay. So when you look at the symbolic picture here on the slide, you'll see a single channel from the switch and your reset button into the safety relay. But on the contactor, the motor relay, you'll actually see 2 arrows. The safety monitoring relay turns that contactor on, but on the same token, the contactor is going back into the safety monitoring relay. That's your normally closed contact, so we can determine if that contactor is functioning properly or not. If we detect a failure, you can prevent the machine from being able to re-enable or restart again. It's still a single channel system. It's a little bit higher than category 1. So it gives you more manual checks, but gives you some diagnostic capabilities. When you look at it on the pictorial, you can see some wires in here schematically, but this is basically what's happened. You can have a single or dual channel from the interlock switch going into your safety relay. You have your reset button. Some relays may be independent. Some may put them together where you wire them in series with your feedback loop from your motor relay to know that that circuit is functioning properly or not. At the end result, it's still a single contactor that's turning on that motor, turning it on or off. When you see it schematically, you see the symbols. You have your safety monitoring relay with your terminals. So there's a couple different ways of configuring that relay. Here you have a control category 2 in the schematic representation. But you still have your start-stop capabilities, your reset capabilities in a single-channel system. The next step up, which is a big jump in reliability of safety, is getting into control category 3. Control category 3 is a redundant system. You have redundant signal paths and checks and redundancy on your contactors as well. You have to have that redundancy and monitoring. Any single fault in the circuit should be detected by your safety circuit. If you have an accumulation of faults, an accumulation meaning you have 2, 3, 4 faults all occurring at the same time, you may lose your safety functionality. So it's not a full-blown control category 4 like you'll see, but category 3 does have the ability of having the redundancy and monitoring. So in the symbolic slide here, what you see is you see a single safety interlock switch, but you have 2 arrows. You have 2 independent channels of signals coming from the safety relay back into the switch and back to the relay. If one channel fails, the other one still ensures a shutdown of your machine. In addition, when you look at the output side, you no longer see one contactor, you see 2. The reason you see 2 is you do not eliminate the possibility of contactor failure. So if one contactor were to fail and weld, the other contactor is set to still shut down. But because you're using those mechanically linked relays or contactors, they're fed back into the safety relay, and you can detect that single failure of that contactor, prevent your machine from restarting until you fix the failure. So you have redundancy and monitoring. The goal is the redundancy. If one path or one component were to fail, you can detect that and prevent your machine from running and turning it into a single channel type of system. So the higher the need, when you look at the decision tree for control categories or performance levels, the higher the severity a higher frequency of exposure, a higher possibility of avoiding it, you get to that higher safety levels that there's more happening behind the scenes. When you look at the pictorial, similar to Category 2 where you have the safety relay in the middle, but one of the differences, you have two independent signal paths coming from the door interlock switch, and now you have two independent contactors that are driving the motor. Again, if one fails, you see the normally closed contacts in series with the reset push button, that you will never be able to reset that safety relay if you have a failure in one of the contactors. Full schematic, you can see the two independent channels of the door interlock switch as a safety limit switch. Your feedback loop with the motor relays 1 and 2, normally closed with the reset button. And you can still do your normal start-stop all day long on the motor unless a safety circuit has been broken or detect any type of failures. The last control category we're going to talk about is Control Category 4. Control Category 4, when you see the symbolic, doesn't look a whole lot different than Control Category 3. But when you look at the definition of Control Category 4, even an accumulation of faults has to be detected. You're required to do things such as cross-short recognition, meaning if you get a dead short between the channels, which you may not be able to detect in a Control Category 3 system. It all comes back to your design. The contactors still need to be mechanically linked so you can get that feedback loop, whether it's a Type 4 light curtain or a coated magnetic type of switch that can be used in up to a Control Category 4 safety system, gets wired into that safety relay and tied into the rest of your circuit. So when we look at the pictorial representation, you'll see one of the big differences between what you saw in the pictorial of Control Category 3 and what you're seeing on the current slide is, on Control Category 3, you saw one door interlock switch. In Control Category 4, you see two individual safety interlock switches. But both those switches are actually on one door. So you have two switches on one door. Why is that required on a Control Category 4? When you use safety switches that use a mechanical actuator to change the states and rotate cams, for example, or a safety rated limit switch type of device, you don't eliminate the need, or I should say eliminate the possibility of mechanical failure. What happens if a key breaks inside of the switch? Well, one single failure can lead to the loss of the safety function. With a Control Category 4, we can't allow that to happen. So on electromechanical switches that use a separate mechanical actuator, you actually put two switches per door. And the reason behind putting two switches per door, if one key were to break, such as on door 1A listed there, the other key is still functional, but because the key broke inside door 1A, the safety monitoring relay sees it, detects it, and prevents you from restarting your safety circuit again. When we look at it schematically, what you see here is the difference between the one in Control Category 3 is the same thing. On the door switches, you see two independent switches. There is no dash line connected them to represent that they're in the same switch body or housing. They're two completely independent switches. One switch goes to the first channel of the safety relay. The second switch goes to the second channel of the safety relay. That's key on being able to detect certain mechanical failures that can occur in your safety system as well. That's one of the big differences between Control Category 3 and Control Category 4. Now, when we look at some different examples when we talk about safety circuits and related to a specific category, similar components and how you use them can actually achieve different safety circuit control categories. We talked about one of them, the second point here, using a single electromechanical safety switch. Well, if you use one, you can possibly obtain up to a control category 3, but if you use two independent, you can obtain up to a control category 4. The indication of emergency stops, whether you're using locking switches, wiring switches in series, where a lot of people know is daisy chaining. It's a cost-effective solution where if you have 4 doors on a machine, well, the doors get wired in series. It could be redundant channels. What category do you really achieve in that particular case? So when you look at this next slide, we have a couple of different examples here. Here, you will see that you have on the top left just an electromechanical switch with a separate key actuator. Top right, you see coated magnetic switches. The bottom, you have E-stops. All of these are wired in series. Whenever you wire standard electromechanical safety devices, the most that you can ever achieve is a control category 3 on these particular devices. The main reason behind that, whether it's a coated magnetic or an E-stop or a keyed switch, you don't eliminate some of the mechanical failures, but also because they're wired in series, you lose some diagnostic capability. In the case of whether it's the top left or the top right, you see 4 doors, doors 1, 2, 3, and 4. If a fault occurs on door number 1, let's say the first channel has welded or there was a short circuit in that wiring of that particular switch, if all you opened up was door number 1, the safety relay would detect it. But if you opened up any of the other doors, 2, 3, or 4, either at the same time or after the fact, and even before, that failure goes undetected. You can clear the failure out of the system. So there's certain faults that may be detected or may not be detected in a daisy-chained type of system. Not to say that you cannot achieve a control category 4 with a single safety monitoring relay, but in the last several years, safety switch technology has advanced. You can get from manufacturers now more electronic style switches where each switch does its own cross-short monitoring and its own check from one to the next. So in the case where you're using electronic type of safety switches, some could be what's referred to as pulse echo or transponder technology or RFID type of safety technology. You can actually wire those in series and still maintain a control category 4 because of each switch being able to do its own internal monitoring from one to the next and have a final switching element to your actual safety monitoring relay for the rest of your safety circuit. In a case like you see here, when you're using a single switch, and we're just showing 2 different types of electromechanical switches. The one on the left is an electromechanical switch with a separate mechanical actuator, a mechanical key that gets inserted into the switch, rotates the cam, so you have mechanical mechanisms. Any single mechanical failure may lead to the loss of the safety function. So obviously there's some design considerations with mounting and minimizing that from occurring, but it's still possible that it could occur. So the most you can achieve is a control category 3. Coated magnetic switches are electromechanical devices in nature, but they use magnets. They're non-contact. So you don't have mechanical linkages or arms. So using a single coated magnetic switch and based off of how it's installed may give you up to a control category 4. You see some of the notes down there because you don't have the same mechanical failures, and it does come into account the mounting and installation. If a actuator can break off of a door and just sit on top of the switch, the most you're going to achieve is a control category 3 because you still have some mechanical failure. But if the actuator is upside down, for example, if it breaks or it gets sheared off, it's just going to fall to the ground. It's not going to stick to the switch for that particular failure capability. When we say need to consider justified fault exclusions, when you use control category 3, which you may find a lot of your machines may be control category 3 is the design that you need to go with, and it's acceptable for the overall safety functionality. But using a single mechanical switch, how is that mechanical key protected? Are you using the switch as a door stop? Because most safety switches are not designed to be used as door stops. They're designed to be used for enunciation to the safety circuit. They're an indication. Is it getting slammed? Is the keys getting bent up? Are the doors being able to be lift off and the key can get damaged and bent? And unfortunately, many times what happens is if a key gets bent, somebody may bend the key back into place. That happens a couple times. You start fatiguing the metal of the key, and over time that key could eventually break in the switch. But if you've taken special care in design to minimize that, you can design in what's called fault exclusions, where you're potentially or systematically eliminating a mechanical failure based off of design and installation of the key in itself, for example. When we look at the control category 4, I'm going to just reiterate this again with the electromechanical switches. You see 2 switches on a door, and that's because each one are independently. One of the common mistakes that you may see is if somebody puts 2 switches on a door, they still think you put both switches in series to the safety relay. That's not the case. If you wire them in series to one another, you're still back to a control category 3 because one switch can mask the fault of the other one. You need both completely independent to detect the failure on one versus the other. That's how the safety relay detects that. When you look at emergency stops, whether you're wiring emergency stops in series or it's a single emergency stop wired to a safety relay, one of the common misconceptions or interpretations that people may have that are varied is what we were just talking about. We said daisy chaining, the most you can achieve is category 3, but one switch, it might be possible to achieve control category 4. With an E-stop, it's very rare that you can even come close to achieving a control category 4 emergency stop. For one thing, an emergency stop is not a primary safety device, it's secondary. It's also mechanical. It has to be hit, and it's tripping a mechanical mechanism to trip those redundant contacts that are mounted to it. So you do not eliminate the possibility of mechanical failure within an E-stop, but when you look at the other side of it, when you go through your decision tree of determining what performance level or control categories require, when you look at severity of harm, frequency of exposure, and possibility of avoiding it, reality is on a machine, you typically will not get to a need for control category 4. An E-stop is supposed to be used for emergency purposes only. It's not designed to be used as a normal start-stop button to be actuated every 5 minutes. It's there for emergency purposes. You probably test the E-stop or should be testing the E-stop more often than what it's really required. Hopefully you never need an E-stop, but in the cases that you do, it's there, so it's a rare occurrence or a rare occasion that you need to even call the demand for the E-stop. It could be a catastrophic failure. Your core safety system, such as your door interlocks, no matter what the design, maybe a failure has occurred and the machine didn't stop, the E-stop is there as a backup, as a secondary means of shutdown. When you look at locking switches, electromechanical locking switches versus electronic locking switches, such as RFID or pulse echo technology. The one on the left is an electromechanical switch. Just because you have the redundancies in the contacts doesn't mean you can achieve a control category 4. You're still only able to achieve a control category 3 because of that single electromechanical key. The mechanical actuator, that key that gets inserted, you can still have the possibility of mechanical failures if it's not installed and designed in properly. In doing that, you can only achieve a control category 3. To be able to use an electromechanical switch into a control category 4, you typically need a separate switch, a separate safety switch, to be able to determine key breakage of that system as well. Where an electronic switch, like you see the one on the right, you're able to detect key breakage because there's electronic RFID or pulse echo type of sensors in there that when the door separates, whether the key pulled out or not, and you get key breakage, the safety switch is able to determine that, detect it, thus you can get electronic locking switches approved for up to a control category 4 application. So now when we go back to one of our beginning slides, what happens inside the control box, whether you're using standard mechanically linked contactors, safety monitoring relays, programmable safety controllers, safety built into drives for servo motors, for example. They have certain approvals, but it does come back to how the different systems are wired up and interfaced to it. So at this point, I know we're ahead of schedule a little bit with the control architectures. It wasn't a whole lot to go through, but there's a lot of information there and a lot of different ways to view it. So we'd like to open up the questions.
A few of you have already submitted questions, so we're going to jump right in. While our presenters are answering your questions, please take a moment to answer the feedback form that will appear on your screen. If you have pop-up blocker technology, we ask that you disable it so you can receive the form. Here's the first question. What about combining technologies such as mechanical with RFID or magnetic?
It is possible to combine those technologies together where the electronic switches do their own cross-short recognition, and putting the mechanical switches in series with those, you get into a gray area of what you really achieve, whether it's control category 3 or control category 4. When you have that, most of the time you end up only achieving up to a control category 3. And the main reason is it depends on the type of device that you're working with, such as an electromechanical key, that if you still have the chance of mechanical failure, you're only going to be up to that control category 3 safety level. Whenever you're in a debate on interpretation, you always err on the side of caution of what you really achieved. So it really depends on existing versus new. Do you replace switches or brand new switches? Are you interchanging with those? So it is possible to wire switches in series, both electronic and coded magnetic switches in series, and do have the possibility of obtaining a control category 4 as long as they're in between and the electromechanical switches are not wired in series together so the switch before it can detect those failures.
Your presentation only mentions control categories. Do you mean PL levels or SIL? I thought control categories were no longer used.
That's a common misconception of when the new standard ISO 13849 came about. ISO 13849 replaced the European standard EN 954. EN 954 is where control categories came from. And one of the misunderstandings or misinformation that is out there is control categories have gone away and they're replaced by performance levels. That's not completely true. Control categories are an integral part to achieve a performance level. Your overall goal now with ISO 13849 is to achieve a performance level. So when you look at that decision tree when we showed in the beginning slide, what you saw was a chart on severity, frequency, and avoidance, and it got us into a performance level. But your first step in achieving that performance level is figuring out what control architecture, what your design of your safety system is going to be, because certain performance levels require a minimum of a certain control category. So control categories have not gone away. And this is why we focused on this particular presentation today in this webinar on control categories, because there's still a lot of either misinterpretations or understandings on what we really achieve or how do we achieve this. To get to that performance level, you have to have your core. You have to have your design of your control category. EN 954 revolved around control categories, and it kind of stopped there. But over the years, what everybody has learned is there's more than just how something's wired. It's also the hardware reliability and the overall design of the safety system and your possibility of failures that are occurring. So the control categories are what's referred to as your deterministic approach, where you're determining how your machine or your safety circuit in particular is going to function. And then there's the probabilistic approach, where SIL levels look at is what is the probability of a dangerous failure occurring in the system. What ISO 13849 did was put those two approaches together to achieve a performance level.
Refer to motor relay 1 and 2. Are you referring to the auxiliary relay or the motor starting contactor?
It depends on your design of your system. And the schematics that you saw, it was a fairly simple system. And let me mention again that the schematics aren't complete because you'll have additional things such as fusing and thermal overloads for motor starters. But the presentation is just showing the concepts and what you're looking for on the safety side of things. But what is happening is it's referring to not auxiliary relays, because your safety monitoring relay is your auxiliary relay. It could be your motor starter. So if you're using a motor starter as part of your safety circuit, that motor starter needs to be, that relay or the contactor portion of that motor starter has to be mechanically linked. If you're using a separate motor starter from the two mechanically linked contactors for your overall safety circuit, the motor starter can be your normal run-of-the-mill motor starter. It doesn't have to be anything special or mechanically linked, but your two main contactors have to be mechanically linked.
What about using one solid-state RFID door switch on a door? Can you achieve a Cat4?
If I understand the question right, one solid-state RFID switch. It's the basic principles of the overall design of the switch. If you're using an RFID switch or a proximity switch, they're not safety switches. But it's an RFID safety-rated switch. The safety-rated RFID switch typically gives you two solid-state outputs, similar to what people are familiar with the outputs of a light curtain, and that runs into your safety relay. So whether it's 1, 2, or however many, you can still achieve up to a control category 4 using that RFID switch. If I misunderstood the question, please type it in again, I can clarify.
How is the required control category determined?
When you look at the decision tree, if you use the ISO 13849 standard of severity of harm, frequency of exposure, and possibility of avoiding it, it's going to take you into a performance level. That decision tree used to be there for control categories to get into a control category, but using 13849, it'll take you into performance level, and inside the standard, there's a chart that shows you a graphical representation of a performance level across the row, and then the columns show you what control categories are achieved in that particular performance level. So, for example, control category B is usually associated with a performance level A, or control category 1, you can achieve up to performance level A. If you need a performance level D, you're typically going to be designing in a control category 3 or control category 4, depending on where the hardware reliability comes in. And I apologize for oversimplifying that answer, but ISO 13849 is a whole different topic on what you do, how do you do it, how do you get there, and how do you achieve that in that particular performance level. But in the oversimplified answer, there is a little graphical chart based off of hardware reliability the performance level you need to get to and what control category you need to design around.
Can you achieve a Category 4 with a variable frequency drive instead of a mechanical motor starters? Instead of two mechanical motor starters?
I hate to do this, but I'm going to defer this answer to a variable frequency drive manufacturer that you would be using. I can only tell you what I typically have seen. What I've seen is they achieve up to a control category 3, performance level D in their ratings, but I'm not going to say that there isn't drives out there that can achieve a control category 4. I'm just not sure about that, but no matter what you do, whether it's a variable frequency drive, it's a servo drive that has the safety on board, the like a safe stop or safe torque off type of feature, always refer to the manufacturer and their installation instructions, because they typically have had that drive approved by some sort of third party like BG or TUV to meet a certain control category and performance level. So when you look at their specs on the safety circuit, they'll give you examples. This is what you have to do to achieve a Category 0 stop and control Category 3, performance level D for your safety system. If you want to achieve a Category 1 stop, this is what you do. So you really got to refer back to the manufacturer of that particular drive. To me, I think it's too difficult to make a blanket statement on whether you can or cannot without consulting the drive manufacturer.
I don't understand why two independent mechanical switches are capable of detecting a key failure. Could you explain further?
When you use two independent switches on one door, it's just like if you think about the concept of the output contactors. If you get the two contactors, can both of those contactors potentially weld? Yes, they can both potentially weld. The likelihood of them both welding at the same exact time, at that same instant that you're switching off, is not very probable or likely. Where one is taking more of the load of the other one, maybe it's a little slower, a little faster, one is going to weld, the other one is still going to shut off, and because they're mechanically linked, you're detecting the failure of that contactor. If you apply that concept to an electromechanical switch with a mechanical key, you have one switch just controlling the first channel. You have the second switch on the door controlling just the second channel. The odds are of having two mechanical keys or two cam mechanisms failing at the same exact time, and at the moment that you open up that door, you have a mechanical key break and a cam failure at the same exact time you open up the door. Not saying it's not possible, it's not very probable. The odds of that happen are astronomical. So what happens is if the first switch, the key breaks off, the second switch, the key is still maintained on the door, opens up and rotates those cams to give you an open circuit. The safety relay sees that the first circuit didn't clear, but the second circuit did. So when you close your door again, the first circuit has never cleared. The safety relay says, wait a minute, one circuit cleared, the other one didn't. Stop, I'm not turning anything on because I have a failure in my safety system somewhere. That's how it's detecting one channel versus two. So if you had that single failure, it does go detect it.
On a rotating load protected by a guard door, which is protected by a locking switch, are two locking switches required to achieve a Category 4?
I'm sorry, Steve, can you repeat that one more time for me? I missed the first part.
On a rotating load protected by a guard door, which is protected by a locking switch, are two locking switches required to achieve a Category 4?
Typically, in my experience and from what I see, you don't need two locking switches. One locking switch is usually sufficient because it's still just a single coil, a single solenoid. But the concept is to detect a failure of the switch locking mechanism itself. So instead of using a second locking switch, not saying that you can't do that, you most certainly can, but normally what you would see is a locking switch and then a non-locking, like a coated magnetic or electronic type of switch on the same door. So you can detect safely with a safety-rated device that the door is open but the lock mechanism never cleared. Because part of a locking function, when you have residual motion such as rotary, maybe it takes the machine 10, 20, 30 seconds to wind down before it comes to a stop. When you have that and you need that door to be locked during that process, you're either monitoring via speed, stop motion, back EMF, encoder feedback, or just simply timing because it's consistent, a safety timer, that you're keeping that door locked for safety reasons. In cases like that, the lock needs to be monitored. And you can get safety switches that monitor just the actuator that are locking switches. You can also get safety locking switches that monitor the lock and the actuator. And that's a big difference. If you get a safety switch that only monitors the actuator and doesn't monitor the lock, you're not using that for residual motion type of applications. That's more process control. You just don't want somebody opening up the door in the middle of a process. But because that lock becomes a safety function, you do need that second switch on there to determine whether you had a catastrophic failure of the safety system with the mechanical key, because in that one instance, even though it may wind down to a stop, but if somebody forced that open and you had a separate failure with a key breakage and that lock stayed locked, you can determine that and see the second switch determine that the lock has failed, and you can shut the machine down safely and prevent it from restarting.
Do e-stop buttons have to have maintain contacts, or can momentary contacts be acceptable, depending on the circuit design?
When you look at the overall design of the e-stop, when you see older machines, you'll see e-stops that are momentary push buttons. I don't want to say momentary contacts, because normally the contacts that are mounted to an emergency stop operator head are spring-loaded type of contact. It's the construction of the e-stop operator head in conjunction with those contacts that makes the safety device. If the question is a momentary push button, there are no momentary push buttons allowed as an emergency stop device. An emergency stop has to be maintained. It has to be a positive self-latching. So you hit it, it latches itself in, and it's either a push-pull reset or a twist-release type of reset. And the reason is the reaction of an e-stop. When somebody has to hit an e-stop in an emergency, it's slap at it. When you slap at that emergency stop device on a momentary push button, one of two things can happen. One, they can hit it, but not hit it all the way. They actually break the contacts open, they stay closed, and they come off of it. The other scenario is they can hit it, and maybe they've broken the contacts, but because it's such a quick slap and removal of your hand, you can break the contacts and make them again, but the circuit behind the scenes takes time to de-energize. Your contactors take time to de-energize. You may not de-energize your circuit and it stays on. Where a maintain emergency stop device actually maintains that those normally closed contacts stay open until you mechanically reset that. When you read any of the standards, whether it's NFPA 79 or ISO 13850 or EN 60204, you have to have a maintain push button, and it has to be that push-pull, twist-release, needs a manual reset before you can start re-engaging or re-enabling the rest of the circuit. So that definitely is a required. No momentary push button is an emergency stop by any standard today. So it's definitely a potential issue as an emergency stop device.
What guidance is provided during the evaluation phase on what level is necessary for the task? Some people may want a Category 4, but do not realize what they are actually asking for. We could be causing design problems when the probability of an event is low?
Your last part of your statement is 100% correct. What happens is somebody will make a bold statement, it's got to be control category 4 without doing any evaluation to it. Well, that's the safe way of doing it. If you design everything to control category 4, you've reached the highest safety level possible when it comes to the safety control architecture. Reality is, the best thing that you can do in any situation is take a step back, look at the machine, identify the functions on the machine. You have an e-stop function, you have a guard door function, you have a muting light curtain function. What are the functions on the machine? Identify each one of those functions and determine what level they really should be at. You can get out of control with safety very quickly. You want to be safe, but you want to have a practical, realistic approach to your design aspect as well. Is there ways that you can achieve category 4 easier than it has been years ago? Yes, with the onslaught of electronic devices, you get more diagnostic capability, you get more wiring and daisy chaining capability to a single, simple little safety monitoring relay, and interface that with safety on drives and things like that. It's possible where you can minimize your costs and get more features, but you can definitely get out of control quick if you're trying to retrofit machines and put all this control category 4 without doing a full evaluation and determine what levels each function needs to be at.
Are there any minimum requirements for a feedback loop? Are there any?
Once you get to a control category 2, if you remember those diagrams, there was a feedback loop when it came to that single contactor. So category B or category 1 is a single channel unmonitored system, so there is no monitoring aspects to it. From category 2, 3, and 4, there is monitoring aspects to it, so you do need to have that feedback loop to determine those external devices. Now, if the load of the machine is small enough that the safety relay can handle, well, the feedback loop is internal to the safety monitoring relay. It's a couple amps, no inductive loads or motors. But that's not the normal situation you run into. You're shutting down motors, you're shutting down hydraulic pumps, you're doing different things on machines that you have to use external mechanically linked contactors, and because they become an extension of that safety circuit, they're required to be mechanically linked, and you need to feed those back in to monitor their functionality. And then if you do not do that, you're not achieving the control category you set out to achieve.
Please clarify when multiple safety switches are connected in series. The second or third press switch are not detected. Does that make sense to you, Mike?
Read that one more time for me.
Please clarify why, when multiple safety switches are connected in series, the second or third press switch are not detected.
All right, I've tried my best to explain this verbally. It's definitely easier to see on paper. What happens is when you have, let's assume that you just have 2 door switches and wired in series with one another. So when you look at a safety circuit, you'll have door number 1, channel 1, wired in series with door number 2, channel 2. That's your first string going to S11 or S12 of the safety relay. Then you have the second contact of door number 1 wired in series with the second contact of door number 2 going to the second enable string for the safety monitoring relay. There's your dual pass. If we go back to door number 1 and let's assume that we get a failure of the first channel. So there's a short circuit. A short circuit in a wire in that first channel, or a short circuit in the switch. Something mechanically has failed in that particular contact of the switch. If you open up door number 1, what will happen is the second contact still opens up, shuts the machine down, shuts your motor down, but the first contact never opened up. So the safety monitoring relay sees a closed loop on that first circuit, and when you close door number 1 again, the safety relay says, I don't want to start because I detected a failure. But now, if an operator goes to door number 2, and they open up door number 2, what happens is, because door number 2 is wired in series with door number 1, you just cleared both signal paths, both safety paths, to the safety monitoring relay. So the safety monitoring relay sees both paths have been cleared and is reset and satisfied. I can restart the machine again. So that's what I mean by masking some of the faults. When you hit the second or third door switch, it can go undetected. The other scenario is somebody opens up door number 2 first, even though a fault has occurred on door number 1. Because you opened up door number 2 first, then open up door number 1, the safety relay is still satisfied. That's why the most you can achieve is control category 3, because certain faults that can occur in the system. But it's also a reason why there's a difference between series wiring category 3, category 4, and some of the failures that can go undetected, where category 4 doesn't allow that to happen, or shouldn't allow that to happen. You need to detect any failure, prevent the machine from running until you fix it.
How do I assure that a press stops when a guard is interrupted?
I think that's a loaded question, and that might be a separate conversation offline. It really comes down to the overall design of the press. Is it a mechanical press? Is it a hydraulic press? Is it a pneumatic press? Is there residual motion? It could be, I'll just use an example of a hydraulic press. Well, maybe it's a down-acting press and you got gravity working against you. What type of valves or hydraulic valves are being used? Are they block centers? Are they recirculating back the tank? Are there redundant valves in case one of the valves has failed? And those are controlled by the safety circuit to achieve your safety control category. If it's a mechanical press where it's a motor, you hit an E-stop, having those redundant contactors to make sure that motor shuts down regardless of what the control circuit is telling it what to do. So I hate to make it vague like that, but it really depends on the design of each individual machine to know how do you assure that the press is stopped.
That concludes today's presentation. On behalf of New Equipment Digest, Machine Design, and EHS Today, I'd like to thank you for joining today's webcast and to thank Mike and Schmerzl USA for sponsoring today's event. Have a great day.